Now I'd like to talk a bit about decoding. And first, I'd like to stress the reverse inference fallacy, which can be very easily summarized by the following example. All dogs eat meat. I eat meat, therefore I'm a dog. There's a clear fallacy here, and it's a clear logical fallacy. It's also known as the fallacy of the converse. The reverse implication is not true. The two premises do not imply that I am a dog. Why is this relevant to the brain? It's relevant because we have so far studied the implication going from behavior to brain activity, but often we would like to conclude on brain activity given behavior.
Gael, just to jump in, there are a couple of questions, so I'm going to interrupt you and then you can come back to this. So the first one is, what is meant by an edge?
So what is meant by an edge? Well, that's actually a very good question. There are many different ways of defining an edge. You can take the conceptual notion of edge. And if you take the conceptual notion of edge, how do you instantiate it? And then there are different ways of instantiating it. And that's basically the state of vision science until I said the mid-90s. It's not clear that the exact definition of an edge matters. There are different ways of defining an edge that will work well to explain brain activity. The definition that I am taking is a Gabor filter, which is almost the same thing as a wavelength. Mm-hmm. So it's an edge detector.
The second question here is, how can encoding be applied in the context of the clinic as opposed to neuroscience? I think here it's like as opposed to sort of basic research.
Yeah, as opposed to cognitive neuroscience. Well, take disorders or pathologies. They're usually studied in isolation. I will look at autism and attention deficit separately. Or I will look at schizophrenia and attention deficit separately. And so, if I do this, I'm going to, and the classical way of doing it is to say, well, I'm going to look at, I'm going to contrast people with autism. And, for instance, I can contrast volumetric brain mapping of people with autism with people with attentional deficit. Or I can contrast people with schizophrenia and people with attentional deficit. If I do this, I'm basically using standard analysis. Now, one way of doing things would be to say, no, I'm going to give a much richer descriptions of my subject. I'm going to describe my subject with many, many, many traits. If I describe my subjects with many, many, many traits, then I start having a high-dimensional description of subjects. And then I will need to start using machine learning to basically predict what the gray matter density, for instance, of a subject is, given that rich description of his behavior, normal and pathological. So this would be one way of doing things in the clinic. I don't know if it's been done. I think it would be interesting to do it. The challenge, of course, is going to have rich enough data. What do I mean by out-of-sample prediction? Well, most statistics tells you something about the data you have. And I'm given data, and given that data, what can I tell on the parameters of my model? That's the classic question that statistics answers, whether I'm going to be looking at a posterior of those parameters, or whether I'm going to try to see whether they can be explained under a null model. What I mean by out-of-sample prediction is, if you were to give me new data that is drawn from the same distribution of the data that I have already seen, how would my model perform? So if I have a classification model, my model is going to separate autism from control. My question is not, given this batch of images, how does my model perform? That is not an interesting question. My question is, if you were to give me new images, what is my expected error rate? What is my expected risk? This is also what we call generalization. Did I answer all the questions?
I believe so for now, yes. So.
All right, well, do not hesitate to ask more. So, going back to my reverse inference problem, if we take a step back and we look at how cognitive neuroimaging works, it's also partly true for clinical neuroimaging. The questions we ask are, what is the neural support of a given function? But a question that we would like to ask often, and that is often discussed in the discussions of papers, is what is the function of a given brain module? Now, the problem is that brain mapping is using task-evoked activity. So basically, brain mapping, the activity that we're observing in brain mapping is conditional on a given task. And on top of this, we cast contrast to isolate effects. But when we've seen this, we've seen only a handful of tasks. So we can, if our task decomposition is right, we can maybe answer what the neural support of a given function is, but we cannot answer what the function of a given module is because we need to reverse the implication. If I've seen that a brain area lights up with, so is activated with faces and not places, I cannot claim that this brain area is specific to faces. I want to claim that this brain area is specific to faces. I need to probe all the possible tasks and behavior on Earth and show that this brain area is activated only when there's a face, in which case I can claim specificity. So the answer to my second question is a reverse inference. It is an implication that is not naturally supported by a given brain, by a given task fMRI experiment. And this is a well-known fallacy that has been very well explained by Russ Poldrak in the 2006 paper. So, is there a face area? It might seem consensual because prominent people have advocated for this, but not everybody believes there is such a simple story that there is an area that is absolutely specific to faces, and it's actually very difficult to establish. So one agenda to answer this question is to use decoding, so basically to predict the behavior given the brain. And the agenda is to then use decoding to find regions that predict a specific aspect of observed cognition. To do this, we will need a large cognitive coverage. We will need to show that activity in these regions enables to discriminate behavior, to predict a specific aspect of behavior across a wide variety of tasks. And so the idea being that to use decoding to support reverse inference, you're going to try to show that some brain regions specifically predict some aspect of the behavior across many different tasks. And then the challenge is that to get such a very wide variety of tasks, you're in a pragmatic way. The best way to do this these days is to aggregate many paradigms and possibly many different studies. And then the challenge is that it's difficult to assign specific description of behavior across those different paradigms because those different paradigms are formulated in a different way. So the basic tool that is used is linear models. And the reason linear models are interesting for decoding is that their coefficients are brain maps. A linear model in decoding has a design matrix that is made by the observed brain activity and is trying to estimate coefficients, so brain map, that are such that the product of the design matrix with the coefficients will predict the target. And so, what people do is that they run decoding using linear models. And so there's a wide variety of different linear models, for instance, linear SVMs, and they look at the coefficients of the linear SVM and they conclude that, where the coefficients are high, the region must be related to the specific discrimination that we're interested in. So for instance, to look at a historical problem, we're looking at faces versus houses, and we're looking at the brain map of a support vector machine. And we're finding that, well, there's loading in this region, so this region must be related to face versus house discrimination. Now I get a different model. There's a wide variety of different linear models, and you can use, for instance, a sparse model. If I use a sparse model, I get only a handful of voxels that discriminates, but my error rate is lower. So I should probably conclude that this is a more relevant brain map. And I can use a ridge. Ridge is another form of linear model. And if I do this, I get an even lower error rate. So that's probably a better model. However, the brain map doesn't look like my prior assumptions. And specifically, it doesn't really outline the FFA or the PPA. So the challenge being here that when we're using decoders and concluding on the brain maps, it's hard to have statistical guarantee on those brain maps because the decoder by itself only controls the error rate. And if we want to put a tiny amount of math on this, the problem we have is that we have an inverse problem where we're minimizing an error rate. So minimizing how many times we get it wrong in our decoding problem, but we have a small number of observations and a very large number of features. So this inverse problem is ill-posed in the sense that many different brain maps are going to give the same prediction error. I can change my brain map, and on the data that I've seen, I will have the same prediction error. And so the choice of the brain maps is driven by the implicit behavior, the implicit prior of the decoder that I'm using. And the decoders, such as SVM, do not have priors that are tuned in any way that are built in any way to reflect something about the brain. And so one example is the sparse estimator, where the prior, I'm not going to go into math, but the prior is basically tells me, try to choose as little voxels as possible that predict well the behavior. And if I do this by construction, I will have a map that is very sparse because it's the prior of the decoder. So a better prior is to use sparsity on the gradients of the image. The reason I say it's a better prior is that a sparse decoder will tend to segment, to select a very small number of voxels. And if you have two redundant voxels, it will select only one of the two, right? I have two voxels, those two voxels are responding in the same way. And the sparse models will detect that they're responding in the same way and will select only one of the two. So if I do this, I'm going to select a subset of the region that I'm interested in. So one way to go around this is to use total variation penalty, which is to say, basically, I'm going to try to select regions on which the spatial gradient is sparse. So basically, I'm going to start to select regions that are locally structured. And this is what we do here. And what you can see is that this segments really well the FFA and the PPA. And so why does this work is because the prior of selecting regions, actually, so what we do here and what we call TVL1 is that we combine this prior of region and this prior sparsity. And the resulting prior can basically be summarized as, please select a small number of voxels that are grouped together that predict well the behavior. And this is well adapted to the intuition of functional units of the brain, which are made of locally connected set of voxels. So if there's one take-home message that you can take from this slide is that different decoders will give different regions. And ideally, I would push you to use a decoder that has a prior that is consistent with our picture of the brain. And the TVL1 decoder is one of these. Now we have a more recent work. So the TVL1 decoder is implemented in Scikit-Learn under the SpaceNet module. And we have, so the drawback of the TVL1 decoder is it's slow. And in Scikit-Learn, we hear about fast models because then they can be used on commodity hardware. And more recently, in the last few years, we came up with different strategies that have a similar behavior, but are much faster. And just to give a quick idea of how they work, and the most recent version is called FREM, for fast, regularized, and Sobolev models. And the idea is that we're going to use very fast models that are suboptimal, and we're going to average many of them. And the benefit of averaging many of them is it gives you very stable maps. And to capture this idea of functional units, what we're going to do is that we're going to learn parcellations of the brain by some fast clustering. And we're going to estimate linear models on those parcellations, and we're going to average the result. And we can do this many times, and each time we're going to perturb a bit the data. And so each time we're going to get slightly different parcellations, and so slightly different sparse linear models. And the result is basically a combination of all this. So if we do this, we get a prediction score that is the best performer compared to, so these are empirical results that have been done across many different decoding tasks. So we get a good prediction score, but unlike L1 models, we get much more stable brain maps. And the reason is that L1 models predict well, but they tend to select a subset of the voxels. And see, the subset is very, very unstable. I might select this voxel or this voxel. So randoming this one or this, it gives me a very unstable model. The FREM will group these together and enhance them. So I get much better stability than the other approaches. And I get a computational speed that is quite comfortable, so slower than SVMs, but significantly faster than the other spatial models. So
yeah, can I stop you here, because there are a few questions that have come up, and
sure.
I'd like to sort of try to address those. So I'll start maybe with Ben asking, maybe I'll start with the more specific, and then I'll go to this general question. So Ben asks, if you run several decoder strategies of the same data to see which one fits best, do you need to correct for multiple comparisons?
That's a very good question. That's actually, you should. You really should. However, so the way, I haven't gone into the methodology of machine learning. The way this should be done, according to machine learning principles, is that you should separate your data, and you should hold out data. So leave data untouched. You should run your analysis, including cross-validation, and select your best model, and then test this best model on the left-out data. Multiple comparison works for p-values. So you might, conclude that, oh, out of these three models, there's no significant difference, which would be a very good conclusion. And then the question is, how do I now know what is my actual prediction performance taking the best model? I take out my left out data, my held out data, and I take my best model and I apply it to this held out data. This is how you should do it. It's the same problem as multiple comparison.
Another question here is, when using the TV decoder, are the features flattened like in L1 and L2 models? If they are, then how do you compensate for loss of spatial and okay, not entirely, some kind of spatial information here?
Well, they're smooth. They're not flattened. They're smooth in a way. It's the intuition of sparsity in the gradient is actually slightly incorrect. I don't want to go into details, but it's more of a smoothing on the gradient of the image. And I claim you don't lose spatial resolution because I claim you don't have this spatial resolution. This is controversial and MR physicists get annoyed. But if I've seen the response to a brain image, to a given task, only 100 times, my limit to my resolution is not how many voxels I have in my image, how many times I do a task. And now, if you make the hypothesis that those voxels are all independent, then you can use mass invariant analysis and you can do the analysis on each voxel. And then, sure, you're not too limited by your number of stimuli presentations. But if you make a multivariate analysis, then you're most often limited by your number of stimuli presentation. So you don't have that solution.
Okay, Ben asks also, when one does decoding, can you decode performance on behavior A while controlling for performance on behaviors B and C?
Oh, that's an interesting question. We would get in a very long discussion there.
So maybe, you know what,
Because
let's maybe not, let's punt this one and say, let's ask this one on
okay,
Slack also, and then move on with your lecture. There is one more question. So Ben, I'm sorry, but let's take this one on Slack. And or Neurostars, if you're watching this later on, we can also ask this on Neurostars. The question is, could you give a brief explanation of the different machine learning models and in which scenarios it is best to choose each one of them?
so well, machine learning models, there is a gazillion.
But maybe of the ones that you're showing here, like SVM versus GraphNet.
So if you're getting brain images, if you have inputs that are brain images, most likely you want to use linear models. First thing, because you have way too many features compared to the number of samples, and you want to stick your model. These are what are going to predict most, unless you're in very uncommon situations with extremely large cohorts. By extremely large, I mean dozens of thousands of individuals. Now, which one should you use? My bias is you should use TVL1 or FRED. And I think it gives a very good benchmark, but never trust a scientist on his own results. Always check them. Now, it's a bit of a problem because the more models you're gonna try, the more you risk to overfit. So ideally, I think what we should have is an independent paper validating our biases and showing that these are good models. But what we found is that fMRI are the best models.
Cool. Oh, and then one more question. What are essential differences in machine learning processing EEG data compared to voxels? Maybe let's take that one as a discussion question later on. So Alex, sorry, but I'll punt that one to later and come back and ask that one again later on, or I'll leave it open for now.
I don't know if we have a half hour after my course, but I'll be staying online if people want to discuss things.
Yeah, we can, after we log off, you can stay on Slack and answer more questions about these things. Okay, so you can go ahead and continue.
Okay. So, but which model should you use? The answer is on the slide, and in the paper, on the front paper, you should use the FRED model. I'm biased, but please confirm my biases. Okay. So if we have time, we'll play with these things on the notebook. We'll compare those models on the notebook once I'm done with those slides, which also tells me I need to move faster. But I'm getting to the end of my lecture. So, all the questions on the validity of machine learning, whether they're on which model we should use, which parameter we should set, or do my results generalize, all these are done or answered using machine learning methodology, which is basically cross-validation, and the idea being that you're going to test a given model and see data. The whole validity of machine learning is based on this. And yes, sometimes there are theoretical arguments that allow you to say certain things, but honestly, in my opinion, they're brittle. They don't apply robustly to neuroimaging data, and the validity of machine learning is based on cross-validation. Now, there's one caveat, is that if I don't have enough data, cross-validation becomes brittle also. And to give you one example, there was a Gael competition that was run a few years ago to predict schizophrenia based on fMRI. And this Gael competition had two left-out data set, as often with Gael competitions, a private data set that is never shown to the competitors, and a public leaderboard where the results of testing the model are shown. And what I'm showing you here is the distribution between the observed error on the public and the private leaderboard. And so, this distribution basically ranges from, well, has significant mass from minus 15% to plus 14%. When you think of it, that's pretty huge, because that's a 30% difference between, well, the 95% confidence interval are plus and minus 30%. So plus and minus 30%. It tells you on the same data, I could have 50% chance of prediction, or 70. I could be reporting this. Why is this? Quite simple. the size of the test set were 30 and 25. So they were tiny test sets. Tiny by the standards of machine learning, not tiny by the standards of brain imaging. And by the way, in this competition, the person who won the competition was the first submission ever written. So first person writes something, sends the code, wins the competition. So all this is well explained if we think about the sampling noise on the test set. And this can very easily be modeled by binomial law. The idea being my classifier can be modeled as a coin flip, but ideally a biased coin flip, because if it's not biased, it's choosing at random both options. So my classifier error can be modeled by coin flip. And so if I have only 30 subjects in my test set, I'm flipping the coin 30 times. And flipping the coin 30 times does not give me a very good estimate of whether the coin is biased or not. And so these are empirical distribution of the error for 30 subjects, 100, 200, 300, 1,000. And I'd just like to stress that the confidence intervals are bloody large. And even with 1,000 subjects, the confidence intervals are plus and minus 3%. And most papers that I see that claim that they have designed a new method that improves machine learning, including mine, by the way, that improves machine learning on brain images do not have an improvement that is greater than 6%. That's a pretty huge improvement. So most of these improvements are adequately explained by chance. So that's quite a disastrous a consequence on the field, because it means that methods researchers like me are very likely to report models that look good but are simply this seemingly good performance is simply explained by chance. And so the way, by the way, we've gone around this is to do benchmarks across many different experiments, which increases the sample size. So that's for methods results. And for application results, there's a very big danger is to test a bunch of different approaches. For instance, all the decoders that I've mentioned before, and pick the best one. In which case, the problem is that you're mining the tail of this distribution, and in which case you can't trust your results anymore. So there are two ways out of this. One is to stick to standard models and really only use these. The other one is to have larger data sets. Ideally, we should do both. And those standard models should be established by thorough benchmarks across many different data sets.